Hello, thank you for joining me today. My name is Derek Manning. I'm an undergrad research assistant at Elizabethtown College, and I'll be presenting our work on ACETA, Accelerating Encrypted Traffic Analytics on the Network Edge, which is a joint collaboration between Elizabethtown College, the University of Massachusetts Lowell, and Intel Corporation. Here's an outline of what I'll be covering in this presentation. Starting things off will be a brief introduction to encrypted traffic analysis and why it is relevant. This includes the different methods for conducting traffic analysis with both their advantages and disadvantages. Next, I'll talk about where our research fits into the grand scheme of things and how our solution aims to solve the drawbacks of some of the existing solutions that are out there. Then, with these goals in mind, I'll dive into the structure of ACETA and also cover some of the different methods for accelerating the analysis pipeline. Lastly, I'll share some of our experimental results we've obtained through initial testing on a real-world data set before wrapping things up. Encrypted traffic has grown over the past decade to the point at which today it occupies the majority of internet traffic. According to statistics reported by Google in 2019, 94% of Google web traffic was encrypted, and the number of encryption certificates issued per day was over 1 million. And while it is a good thing overall that more people and enterprises are adopting secure protocols, this technology also benefits malicious users as they try to keep their activities hidden. With malicious users shifting in recent years to using primarily encryption-based protocols as well, it has become important that administrators and security tools be able to identify malicious activity despite encryption. Traditional solutions for identifying network threats fall into two main categories, which are deep packet inspection and offline pattern modeling. However, deep packet inspection is not applicable to encrypted traffic unless you have the means for decryption. And if you do have these means, inspecting decrypted data will compromise user privacy and data integrity, not to mention that this would also be computationally expensive. Previous research done by the creators of the Cisco Joy Network Data Feature Extractor has shown that by monitoring malicious behaviors on a session-based level, offline pattern modeling can achieve high accuracy with low false positives. However, training machine learning models and inferencing in a timely fashion is challenging due to the high computational power requirement of machine learning models in general, and the low latency requirement for the inference of such model in a live network environment. As mentioned before, the Cisco Joy package is a valuable tool for extracting network data features from either live network traffic or packet captured files to be stored in JSON output files. We leverage Joy in the pre-processing stages of ACETA to generate structured data from raw network flows, which I'll return to in a bit. These reasons lead into the motivation for our work. Our first goal was to design our solution to implement Intel performance libraries that are designed for accelerated execution on Intel hardware. The Intel Data Analytics Acceleration Library is the primary library that we use for this purpose. This library offers highly optimized functions for all stages of the analytics and machine learning pipeline with support for several different languages. Intel also offers the OpenVINO toolkit for use with image processing and deep learning, which we leverage for neural network implementation later on. Another one of our goals was to offer a variety of model types for our package to offer a diversity of choice for our users. And our final goal is to conduct a performance comparison of the original Joy implementation against the accelerated and optimized ACETA implementation, comparing the speeds and accuracy for training and testing. The structure of ACETA is separated into several different stages. First, we have the raw traffic data, which can either be a live network flow or in PCAP format, and pass this information to Joy to extract the different network features. Due to the potentially large amount of data at this step, we offer the capability to split this up using multiprocessing, which can yield significant speed up in terms of processing time. Once the raw data processing is complete, we are left with an assortment of JSON files corresponding to each individual flow, containing an abundance of network feature information. We further process this data down into the separate TLS, DNS, HTTP, and metadata categories using the JSON files generated by Joy. In this subsequent processing, we condense the network flow data further into corresponding JSON files for each feature of the flow. So the final processed data will consist of 4 JSON files per flow. And again, at this step, the user can specify multiprocessing to accelerate the data parsing. A benefit that splitting the data corresponding to the different network features into different files is that come time for model training, this allows users to control whether they want all network features to be included in training or to only use a subset that might be enough for a given application. After the data is processed and ready, it's just a matter of selecting which features to include and what kind of machine learning model to train. Currently, we offer 4 different machine learning models. From the Intel DAL library, we implement logistic regression, decision forest, and support vector machine. And from the Intel OpenVINO toolkit, we use a neural network. Once a model is trained, it is saved to disk, and upon running ACETA for inference then, the specified model will now be loaded to make predictions on samples. As stated previously, the feature extractor of Joy extracts TLS, DNS, HTTP, and metadata features from network flows. The TLS features include client advertised cipher suites, client advertised extensions, server supported cipher suites, server supported extensions, validity of server certificates, client public key length, and whether the certificate is self-signed. The DNS features are composed of contextual information related to the encrypted flow, such as the length, suffix, most common TTL values, and number of non-alphanumeric characters, to name a few. The HTTP features consist of the header data originating from each source IP. This includes the presence of inbound and outbound HTTP fields, the content type, user agent, server, and return code. Lastly, we include some metadata features denoting the interpacket times, interpacket lengths, and the overall byte distribution. Pertaining to acceleration, I've mentioned before a few methods that we have implemented in our design. First and foremost is the Intel Data Analytics Acceleration Library. The Intel DAL library provides optimized data processing and machine learning functions targeted specifically for Intel processors. These library functions maximize processing speed by knowing the instruction set, vector width, core counts, and memory architecture for each processor that they run on. And similar to the popular scikit-learn library, DAL offers support for many of the popular machine learning algorithms. Using these algorithms, we're able to accelerate both training and inference time in the ETA pipeline to be several magnitudes faster than the standard library alternatives. Another method for acceleration used in ACETA is the Performance UltraJSON library instead of Python's standard library JSON module. UltraJSON is significantly faster compared to the default module due to it being written in pure C with bindings for Python. With a large number of reads and writes relating to JSON, this amounts to a significant performance boost. And as mentioned in the previous slide, we also use multiprocessing to speed up the data processing stages. Comparing the DAL version code with that of scikit-learn, which typically would be used in this situation, there are many similarities. This example shows the code to implement a simple logistic regression model for training, then testing using each of the libraries. Both modules implement the same general pipeline of first creating a model, object, training the model, then predicting using the trained model. This similarity makes integrating DAL into programs using other libraries as simple as possible. In evaluating ACETA, we use the CIC and MAL 2017 dataset provided by the University of New Brunswick. In addition to benign traffic, this dataset contains 4 categories of malware, which are adware, ransomware, scareware, and SMS malware, with samples coming from 42 unique malware families. Comparing the baseline with ACETA first involves randomly splitting the subsets of the process data for training and testing, providing 1 sample from each of the malware families per subset, along with many more benign samples. The subsets are partitioned, then saved to files to be shared by the baseline and ACETA for a level comparison. We use the standard Python time library for timing of the model training and inference, and we measure the accuracy by using the labels of 0 and 1 for benign and malicious samples respectively. Performance statistics are gathered using the Python C-profiling utility, along with the K-cache-grind tool to process and present the data. The platform used for testing was a Linux machine using Ubuntu Desktop, featuring an Intel Core processor, 16 gigabytes of RAM, and the latest versions of Intel DAL, OpenVINO, and Anaconda Python. The first metrics we gathered were the training and inference times for the baseline and ACETA versions of each machine learning model. For all models except the ANN, the ACETA versions outperformed the baseline by several factors. Logistic regression was 10 times faster, decision forest was 3.25 times faster, and SVM was 31 times faster. However, a 100 epoch neural network comparison results in the ACETA version being around twice as slow as the baseline. One reason for this is that for training in the ACETA version, we chose to implement a simple Keras TensorFlow model for the sake of simplicity. DAL does offer low-level APIs to design neural networks piece by piece, but we chose to use Keras for training the initial model. And then later on, we would optimize this model for inference using the Intel OpenVito toolkit, which resulted in a faster inference time relative to the baseline overall. ACETA also performs significantly faster for inference in each of the models. The baseline models all completed in a little over 9/10 of a second, whereas ACETA versions took on average around 20 milliseconds, which is a speed up of around 45 times. Next, taking a look at the resulting models' accuracies. On the training data, predictably all models achieved high accuracy, and inferencing on the test data also achieved good accuracy in all models for ACETA and the baseline. Overall, the performance shows very little difference between the two versions, with the average difference being around a single %, despite the large gains in speedup times that we have seen in the last slide. The final step in evaluating the model performances was to study the breakdown of time for each model in the stages of their execution. We leveraged the C profiling utility to track and save the cumulative time the program spent in each of its functions. Then using the K-cache-grind tool, we visualized the data to locate major hotspots within executions. For the majority of the models, the training of the models occupies the largest percentage of time, which is to be expected. So with the acceleration of DAL and OpenVino, the ACETA versions in general receive a decrease in the training time percentage overall. In conclusion, the rise of predominantly encrypted traffic on the internet has led to a rise in the use of encrypted traffic for malicious activities. For this reason, the analysis of encrypted traffic has become an important topic to study. We have shown through our research with ACETA that using Intel performance libraries, we are able to accelerate ETA significantly with very little sacrifice to performance, which is important because as systems are further developed for ETA, they must be able to do so in a timely fashion as to not introduce excessive delay time into the network traffic. Before wrapping this talk up, I'd like to take the time to thank our supporters for the ability to work on this project, the National Science Foundation, Intel Corporation, and the Scholarship, Creative Arts, and Research Projects program at Elizabethtown College. This concludes my presentation on ACETA. Thank you for joining me today.